una cosa in testa e... Hello again.
Hello.
It's the same people of the last workshop, unfortunately for you. We are now going to talk about how we can use compositional game theory, which for the people that weren't here in the last workshop is a way of doing game theory using basically Lego bricks to make sense of PBS, which is proposer-builder separation, which is a kind of hot topic in Ethereum right now. Okay, let me do a recap. So what are order flow auctions? Okay, so basically, as you probably know, with the passage to proof of stake, the infrastructure of Ethereum is changing quite a lot. Basically, in the last years, stuff like MEV has surfaced. People got aware of the fact that the order in which you put transactions in a block is really important and valuable and can be used to basically make money or steal money or stuff like that. So this created a much more diversified environment in Ethereum. And it's not anymore the case that you just have a miner that takes the transactions from a mempool and creates a block. Now you have what are called proposers that are basically block space providers. So these are actors that a way or another have the power of providing the block space. Like if you are elected proposer in Ethereum, you have the block space and you can fill it in basically any way you want. Then there are searchers and block builders. These are actors that in principle do not have the block space, but block space is valuable for them. These can be, I don't know, like MEV bots, bundle builders, basically all the actors that can package transactions into a bundle or into a block, and if that block lends it on if that bundle lands in a block, they can basically make money out of it. So, I mean, builders and proposers and searchers can actually be the same actor, but, conceptually, they are really separated roles. And now the idea is that proposers have the power of giving away block space, and searchers and block builders are actually interested in getting this block space to fill it with whatever transactions they want. So this created a system where searchers or builders actually could bid for block space from proposers. And then they have to make sure that they get the best transactions to populate their blocks so that can actually make money out of this. So you have an outflow of money if you win the block by bidding, and then you want to make some money, like with MEV or with fees or whatever, to actually recoup. And the idea of PBS is exactly creating this system where, block proposers can auction this space in a standardized way to builders. The cool thing about this whole system is that now the agents that create the transactions, which could be the users or order flow providers like DEXs, are in a powerful position. Because the idea is that if you create a transaction from which a lot of MEV could potentially be extracted, then you may be interested in saying, hey, Mr. Builder, why don't you make me a proposition and I give you the transaction, and then you get the MEV out of it. So basically the idea of order flow auctions is that in order flow auctions, the builders not only bid to proposers, but they also bid to users. So they are kind of saying, if you come to me, I will give you the best deal. I will redistribute some of the MEV to you. It really depends. Like there is a constellation of services that are being offered. There are various like RPCs popping up, privacy preserving RPCs, RPCs that basically guarantee you that if you're not included in the block, your transaction is not, your bundle is not leaked, etc., etc., etc. Now, the point is, it's still quite early, but and we already see that with PBS, basically, block space is being auctioned by proposers to builders. There are still a lot of ideas around which auction mechanism works best for PBS, because when I say proposers auction transaction block space to builders, what do I mean? There are a lot of different types of auctions that you can use. And in general, at the moment, with order flow auctions, the space is still quite uncoordinated. There are a lot of propositions. One of the propositions that is getting traction out there is this idea of intent-driven transactions. The idea of an intent-driven transaction, like in a nutshell, is that in a standard transaction, I just tell you, hey, I want to call this function from this contract, and I want to do this. And you, the block builder, just take this thing and put it into a block. The idea of an intent-based transaction, really hand-wavily, is I just give you a goal. I tell you, hey, I want to exchange this much from this for this much. I don't care which DEX you use. I don't care how you do it. I leave all these details to you. And now the idea is that block builders, the more skilled it is, the more is able to honor those constraints by, making a penny on it, by basically making money on it. And in general, we are still not completely understood how all these things interact with each other. So this is, in a nutshell, what is going on in PBS land up to now. Now, what are open games on the other hand? Well, you can go back in time and follow this morning's workshop if you want, but if you can't do that, I will give you a very fast recap. An open game, open compositional game theory is basically a way of doing mechanism design in terms of systems and processes. The idea is that we represent mechanisms as open systems. So a game is a box like this. It observes some stuff, so you have some input from the past that are the observation. The game does some strategic decision and outputs an action that gets forwarded into the future, into a context. This action will have consequences. So the game will observe something from the context. This is, for instance, in Prisoner Dilemma, if you play Defect or Cooperate, you are going to get a payoff. And then the idea of this wire here that we call the feedback wire is that you can redistribute these consequences into the past yourself. So the idea is that you as a game are framed into a context, but you as a game are also part of the context for whatever is on the left and on the right. Okay. You can compose games. If the types match, you can compose them sequentially in this way. And you can compose them in parallel. Composition is probably a weird word that we call it parallel composition, but the idea is that you are just considering two games at the same time, but they don't share any input and any output. You're just saying these two games are happening at the same time. Okay. Now, all this stuff has been implemented. We have a DSL embedded in Haskell. We will show it to you. It's freely available, and we used it for designing a lot of applications around PBS, taking protocols, token designs, and whatnot. Okay, so what is the basic design that we are going to see today? The main idea that we are starting from is that this PBS world is probably will become increasingly more complicated. At the moment, you see block proposers auctioning block space to block builders. But for instance, you can imagine that the block builder may itself fragment that block space and run auctions to sub-builders, to basically smaller players. Imagine that you are running some kind of niche service. You cannot fill a block by yourself. You have a smaller bundle. You may have an interest in participating in an auction for a fraction of the block space. So the kind of basic design that we are using here is the idea that a player in our design is at the same time an auctioneer for all the players below it, and a bidder for all the players above it. And in this way, we can recursively build these kind of complex systems. So, so this is exactly what we want to do. We want to use this interconnectedness provided by open games to make sense of order flow auctions. Okay, so this is the basic building block that we are going to use. We are going to chop up the players in layers. The idea is that every layer, again, you can see it as a game, and these are the internals of the game. So what happens is that some inputs from a layer below are coming in. These inputs are copied to each one of these blocks. Each one of these blocks is a player that plays on this layer. Each one of these players is taking some decisions depending on the inputs. These decisions are all concatenated together, basically into a list, and they are forwarded to the next layer. Then the payoffs or whatnot come in from the layer above. This could be, for instance, bids in an auction, and these are the results of the auction. These results are copied to all the players, and these players themselves, I'll show this in the next slide, but if you consider a player as at the same time a bidder and an auctioneer, the idea is that here you are bidding, you are receiving the result of your auction, if you won or not, but you're also an auctioneer, so you are getting the bids from players at a lower level, and now you gotta tell them, hey, you won or you didn't win. So you have this kind of thing, and this is, by the way, how you implement this in our DSL. We will show the code in a bit, but the idea is that, you see, this thing here, so this is the code. Let's zoom in. So these two things here are basically these two games here. This game, again, is taken the inputs and is not doing anything with it because they are automatically copied to all players. But this thing here, you see, this thing here is taking a list of feedbacks, so these wires for all players, and it's concatenating them into a list that spits out here. This thing here is doing the opposite. It's getting the outputs of all players and is, concatenating them and routing them into the future. These things here are the players. Again, each one of these players sees these bunch of inputs, does something. This is basically the player. I will show this in detail in a second. Spits some outputs, gets some returns, so the outcomes of the auction when this player is considered as a bidder, and spits back in time the result of the auctions for which this player is an auctioneer. Now, how is a player modeled? This is a player, an agent in this model. So, if you see here, we are basically taking these inputs and we are copying the same input to all players. Now, the idea is that in this way, all players see all the bits, also the bits not directed to them. But inside the player, the first thing that we have is this block that basically filters all the bids coming in by discarding all the bids that are not directed to this player. The reason why we model things in this way is that this is kind of the standard behavior, but now by tweaking this box, you can also model asymmetric information. Now I can tweak this box and basically model a player that, for instance, can observe the whole order flow, and so can observe also bids not directed to itself. Now, these bids are coming in, they are filtered. Now, basically, an auction is run on these bids with some auction parameters. This could be reserve price, first price, whatever you care about. Then what happens is that we are basically storing who are the winners of this auction. And we are, basically putting this thing here and waiting with it. Now I will come to why. We are also using the outcome of the auction to basically estimate the payoffs. Okay, from this auction, this is how much money we are actually making. Okay. And then we have a bidding process that is, I have a private valuation of how much my block, my order flow will be worth. I'm sending a bid in the future. I'm using my bid to estimate my payoffs. This is the amount of money I have to spend, basically. Now I get a return. I get the outcome of my auction. With this, I can basically see, you know, I have to take this into account to calculate the payoff. Especially, you know, there are some auctions when you only pay when you win. So if you don't win, this payoff will become zero. That's why you need this. And also you need to know if you won to let the players that bid with you, if they won. Because imagine that I am a block builder and I'm fractionalizing my block space. People are bidding for my block space, but then I don't win the block. Then I got to tell them, sorry, no one won because like I didn't get the block in the end. So that's why we need both the outcome of the auction internal and the outcome of my bid to basically know to the player what happens. Now, in this model, you can see that the betting, the bidding, and the auction are unrelated. In this model, basically, you can place a bid before running the auction. They are completely independent processes. I'll get to this in a second. In this other thing here, instead, I'm using the outcome of the auction to inform my bidding process. So in this case, I am fractionalizing, for instance, my block space. I'm running an auction. I get some bids in. And only then I place a bid myself by using this information. Now again, this is how these blocks are basically implemented. Again, these two things are basically routing. As I said, this little box here takes inputs and basically filters only the inputs directed to this agent. This thing here is basically combining the returns to the agents and the results of the local auction to inform with feedback agents about what happened. And in here, what we are doing is we are getting a bid, and we are basically packaging it into a type where the bid is provided with the name of the bidder and stuff like that. We are getting the returns, and again, we are filtering because we are getting the returns for all the players in the level, and we are filtering only the ones that we care about. And this block here, this is the auction. Again, it receives the input, runs an auction mechanism, and spits out both the expected payoffs and results of the local auction. This thing is the bid. Again, in this case, the bid has no inputs. So it's just a bid. You're just outputting a bid using this private valuation that is an exogenous parameter. That's why it's represented as a dotted. It's basically, for instance, a probability distribution that you give. And this is the payoff thingy that basically takes all the returns from the agent, the value of the bid, and determines the payoff. In practice, things are a bit more complicated than that, but this is, I think, simplified version of what's going on. Okay, so again, this is, if you basically compare this implementation here with the one where you first run the auction and then place the bid, the only difference is this. The only difference is that the bid game actually takes this result auction parameter as an input, and that's the only real difference. Okay. So now with this, when we talk about game theory and mechanism design, there are 3 or 4 things that you can do. The first thing is that you can study them. This is what has been done like in the auction literature for ages. We are not directly interested in that. I think there is a lot of theory out there, a lot of specialists that, you know, took care of that. What we are interested in instead are these 3 things here. and in particular the last one. So the first thing that we can do with a model like this is searching for equilibria. Like, tell me which strategy is the best, which strategy results in an equilibrium. The problem is that for everyone familiar with game theory, you will know that this problem becomes computationally unmanageable very, very, very quickly. Especially with complex order flow actions, like good luck at finding equilibria, it's very hard. Another thing that I can do is I give you a strategy and you tell me if this strategy is an equilibrium or not. So if some player can do better or not. This is computationally much easier to do, but it's still complicated to, I mean, the idea here is that if you give me a quote-unquote good strategy, I can tell you if that strategy is an equilibrium. But what I'm doing is basically I'm delegating the problem of finding equilibrium strategies to you. And if the system is very complicated, almost always this checker will tell you, oh, there is some profitable deviation. This is not the best thing you can do. What we are really interested in instead is simulations. So in simulations, the idea is that you give me the mechanism, the game, and a strategy, and I tell you your expected outcome. The reason why we think this is interesting is because maybe you are one of the players in this layer here, right? Maybe you are this guy here at in some place in the order flow auction food chain. You have some idea, some rough model of how all the other players work. You encode this in your model, you write this down, and then you say, okay, if I adopt this strategy, what is my expected outcome? So you can basically use this to simulate how much money you can make by positioning yourself in some way at some level of this complicated food chain. Okay. Now, sure.
Do you have to specify all agent strategies to make this happen?
The number of agents in this thing is finite but variable. So you can start with toy models, and you can, turn this into a much more complicated system as time goes by, basically. So the idea is, depending on the quality of your information and your computing power, you can make this more or less complicated. I'll show you the code base in a second. So yeah, this is exactly what I was saying. Like, market placement is, if I, for instance, I change my auction procedure. I remember, as a player, I bid, but I also run an auction myself. What if I change it from, I don't know, first price to end price, or I plug in a reserve price or something like that? Will I intercept more order flow or less? I don't know. You can simulate this. Another thing you can do is best path. So that is, imagine that I have to reserve X block space, and I expect to intercept Y order flow. Would it be best for me to bid directly to proposer, or to maybe participate through an intermediary into a fragmented order flow auction? I don't know. You can simulate it. If you are a user and everything stays the same, what should I do? Should I bid? Should I place my bids to everyone, or only to some players in the order flow food chain? In practice, this, for instance, means if I have a transaction, do I place it on the public mempool, or only on one, on Flashbus RPC, or maybe I want to go through Flashbus and Manifold at the same time? I don't know. You can test and simulate this. Okay, so yeah, we simulate this together with the guys at Flashbots. We simulated different auction mechanisms in the context of PBS. This is basically where this project was started. And what we are going to see now is this little example of an order flow auction. So what happens here is that there are 3 users, 3 builders, and a proposer, okay? So now the idea is, remember that in the idea of order flow auctions is that the builder bids to the user to get their transaction, right? So now, you have these 3 users. These 3 users are basically sending this is not really a bid. They are sending basically information. They're saying, hey, I have a transaction that is worth this much. These builders here will run a trivial auction, so they will just not name any winner, because that's just information that gets disclosed. But based on this information, they will themselves place bids to proposers and to users. So they can say, okay, user 1 says, I have a transaction that is worth this much MEV. Builder 2 says, okay, I am interested in this transaction. I am bidding for this transaction. At the same time, they have to send a bid to proposer, because they have to ensure that they get the block space. And you already see that this is not easy at all, because basically you have to take care of 2 auctions at the same time. You have to take care of securing the order flow on one hand and securing the block space on the other. What happens is, for instance, you get the block space, but you don't get the transactions. Or what if you get the transactions and you don't get the block space? So yeah, this is the forward flow, as I was saying, the red one, and the blue one is the backward flows. So the idea here is that user gives you information, you place a bet to proposer and to users. Now users and proposers basically have to decide which bid they have to accept or not. These are trivial bidders. They don't have anyone to bid to after them. This is the kind of top of the food chain here. So basically the output is just like gets spiked back, and now proposer replies, okay, like builder 1 won, for instance, and user 1 says, okay, builder 2 won, whatever, and that is information is routed back to the end users. Now, the cool thing is that in our framework, you have this trick that when 2 boxes have the same name, you can basically sum their payoffs. This means that what user 2 gains here, it also gains here. This allows user 2 to think strategically forward in the future, because user 2 doesn't really get, user 2 at this stage doesn't really know how much money it will make from the offer of builders. But it knows that in the future it will know. And so since the payoffs of user 2 in the past and user 2 in the future are connected, and same from user 1 and from user 3, you can have an organic game, basically. So the idea is that these players and these players are actually the same players, but at different stages of the game, they have to take different kind of decisions and run different kind of processes. Yeah, and I think now we can basically show the code that we have.
Yeah, okay.
So
let's show a little demo. I understand this is hard, but yeah, the model is here for you, and we're here for you. We made the model, so yeah. Hopefully this will shed some light. Yeah. Okay, so.
So this is files called components, and basically in here, we are just defining all the components in those big pictures that we were showing. So for instance, all these go up 1 second. So these routing sub-games are basically games with no strategic content that see like all the bids and filter them. So for instance, you see this routing, agent routing, pause feedback, weird names. It sees all the returns for all the players in a level. It gets the player name and it spits out only the returns directed to that player. So this is like kind of the filtering, piping infrastructure, the plumbing that makes things work. Here we have auction mechanism. This was the A box in our model. And the idea is that you pass the auction function as an exogenous parameter. So basically, this thing will take the inputs of all directed to the agents, input agent name. It will run the auction function, and it will spit an outcome. With this, sure. They are not predefined, so that's exactly the nice thing. This thing and this thing here will have a type, an Haskell type, and now an auction function can be any function you want with that type signature.
But it would be kind of cool if you had like a library of pre-established.
That's exactly what we're going to do.
We
exactly,
already have them.
For less experienced
Exactly. So the idea is that in this way, once you have a bunch of possible auctions, you can swap them on the fly. Exactly, yes. So if we go all the way down, I mean this, yeah, okay, wait, sorry. So this is what we call agent exogenous. This is basically kind of the basic agent. Again, you can basically see that it does some routing. It runs the auction here. Then it determines the auction results for the agents in the level before. So these are, you are getting basically the bids, and now you are determining, getting also your outcome in your auction where you were the bidder, if your bidders won or not. Then you place a bid yourself here, and then there is some more routing here at the end. I know that it's quite complicated to basically look at it right now in this way. It's just like a dumpster fire mountain of ugly code. But yeah, this is basically just the diagram that you saw before in the pictures, like in our DSL. Again, this is the endogenous agent. This is the one that is actually using the auction information to place the bidding. Again, also in this case, basically all the quote-unquote relevant stuff, all the meat of the model is passed as exogenous functions. So, for instance, you are giving an auction function, but you're also giving this update estimate, that is a function that tells you how you have to use the auction results to update your evaluation and your bid. So all these things can basically be developed separately and plugged in and swapped depending on, you know, what kind of simulation you want to do. So
yeah, and we also have examples for it.
Yeah.
So yeah.
So I think, yeah, if you go all the way down, I think there isn't.
We have the.
Yeah. So yeah, in here we basically define. Yeah, in here we basically define the builders for order flow auctions. I think we also have an order flow auction.hs file.
Yeah.
Where basically we use all these building blocks to.
Should I go there?
Yeah, let's see what's there. So yeah, in this thing, you see, we have the layer. So this is layer 1, where you have name 1, name 2, name 3, that will be the names of the players. The user submit transaction is the subgame where the user has to strategically decide to which of the 3 builders they want to reveal the value of their transaction. And this will be a strategic decision, basically. It turns out that there is a dominant strategy here for the user. Since the user only pays to the winning bidder, basically, like the best strategy for this kind of model is tell everyone your transactions. Do not worry. Again, in practice, we'll see later things become more difficult when you consider intents, when you consider privacy, and all this kind of stuff that we are trying to bake in the model. But yeah, in this simple model where transactions just have an intrinsic utility, that means if my transaction goes in the block, I'm gaining this much utility from the fact. The only thing you want to do is maximizing your chances of getting in the block. Okay, so this is the 3 users, basically. If you go down to layer 2, in here we will basically have the builders. So you will have the builder, the builder, the builder, that will receive the inputs from the users in layer 1, will do all their kind of stuff, and they will spit out their outputs to layer 3. So if you go to layer 3, you will have the proposer, and again, the 3 users that now have to decide which offer they want to accept or not. Now, when you compose everything together, if you go all the way down, there is something called complete game. Yeah, this one. You see, in the complete game, we are basically just plugging the 3 layers. Again, see, like, this spits out outputs 1. This uses this outputs 1 as an input. It spits out output users 2, output proposers, and these are used as inputs in layer 3. So it's exactly the wiring of the picture we were showing before. And now if you go in main, there is basically the simulation function that allows you to run this monster. Yeah, sure. Yeah, I mean, in this case, we just use 2, but in theory, there are ways to scale it to an arbitrary number of users. Obviously, one sad way of doing it is by hand, but in theory, you could use like template Haskell or stuff like that to basically generate arbitrarily big chunks of code. Okay, but yeah, this is basically an ergonomicity problem of which we are very aware. So this piece of code is not even public yet at the moment. It's really a proof of concept, but yeah, for sure, we have to basically make it easier to use. Okay, so now we have a bunch of possible simulations. So the first simulation is scenario symmetric. In this scenario, basically, all builders have access to all order flow. So all users can broadcast their transaction to all builders, and all builders have access to the same information. So if we run this thing...
Already did.
Okay, you already did it?
Yeah.
Nice. You can see this thing spits out some JSON that is basically telling here for each builder how much it costs the builder and how much the payoff is received. Unsurprisingly, since this is a symmetric case and all builders have access to the same information, they basically run all the same strategy and they have all the same expected outcome. Just a word of caution, these games are Bayesian. So when I say expected outcome, I basically mean expected outcome in the sense of probability distributions. So in the end, it is true that only one builder will make it into the block. But then the idea here is that all these builders can make it into the block with equal probability because they are adopting the same strategy with the same information. So that's why you see the same parameters. Basically, these are estimates. Probabilistic estimates. Okay, now, if we go to this one, in this simulation here, basically you have that only builder 3 gets access to the most valuable transactions. How did we do that in practice? If we look at the parameters, I don't know how, if you go to scenario exclusive order flow, I think, yeah, in the parameters, order flow limited, go here, expand this one.
Okay.
Let's see if we can do that. Yeah, basically in these parameters, this is where these things, we are using it to define the action space for the user. So if you remember, I told you that the best strategy for the user is telling everyone about their transaction. But the point is that everyone is an object in a space that you have to define. So in this case, if we are giving this action space, this means that the user at layer 1 sees all 3 builders. And clearly, the best strategy is tell to all 3 what transaction you have. But then we can artificially restrict the action space. So in this case, if we use this one, we are basically modeling a user that only sees the first 2 builders. The strategy stays the same. It says, okay, I'll tell everyone, but we artificially constrained the builders that are available. So the everyone for this user will be limited. In this case, when it's exclusive, when you pass these parameters here, the user in layer 1 only sees 1 builder. And this, for instance, models the idea of a user going through a particular RPC to which only 1 builder has access, for instance. So if we go all the way back to main, to simulation, in this case, we artificially restricted basically which builder sees what. How did we do that? One user had some high-value transaction. We restricted artificially so that that user only sees builder 3. And indeed, if we run this, you see that builder 1 and builder 2 get 0. Like, they don't get any gain and they don't get any cost. Because the point is, since they see less interesting order flow, they cannot place a convincing bet to proposer. Whereas builder 3 can offer more to proposer and basically win the auction. And Okay, so in this other thing, we see the opposite. Now builder tree is only getting access to the lowest value transaction. And indeed, if we update that, let's see if it works. You see now, builder 1 and builder 2 profit with equal payoffs. And now builder 3 is basically fucked because he only sees like the horrible transactions and he will not be able to compete with the other builders with its offer. And yeah, this last one is basically something else that we encoded where basically we tweaked builders so that different builders have different capacities of extracting values from the transaction. So the idea is that for the same transaction, they get different payoffs. And that quantifies like their skill of like exploring the search space for MEV. And when you run this, again, you will get different parameters where basically the most skilled builder that is able to extract the most MEV will also be able to place the best bid to proposal. So yeah, this is just a little proof of concept, I would say. But that's basically what we did. And if we go back to the presentation for a second, I also wanted to show you, and then we go to questions. I also wanted to show you future developments. So the idea is that now we want to stitch this together with intents. So again, the idea of intents and commitments, because they are related things, is I tell you what I want. So the idea is I tell you what I want, and only then, for instance, I show you my real transaction. So a standard example is I tell you, maybe via zero knowledge proof or something similar, that my transaction is at least worth this much MEV. You see this, you do everything you have to do, and only afterwards I show my transaction to you and you have access to the real information. So the idea is that, again, we kind of reused the same kind of block. So we have the first round when all the bids come in, and at this stage, with the bid, you carry the intents, you carry information. Now you say, okay, I care about, you know, in here the type structure will be more difficult. You say, like, I care about this kind of information, I care about privacy preservation, and stuff like that. Then the auction is run as usual. Now, basically, what happens is that after the auction is run, the single user has to decide if they want to provide the actual transactions or not. So some actual transactions come in. Based on whoever won the auction, you decide who to include and how to bundle the block, basically. In here, you can also model things like, I want to cheat. I ensure you first position, but I actually not putting you first in the bundle or stuff like that. After doing that, you can choose to reveal the block or not, and this informs your payoff. This is really interesting because there's been recent publications in which, you know, it is shown that, for instance, there is a difference if the user pays before or at inclusion time. So, for instance, what happens is that if you pay at inclusion time, you may be incentivized to, you know, give your intent to everyone, and then you get a different kind of offers, and then basically you fuck up everyone that is not nice with you and only reveal your transactions to a few selected players. But then in doing so, what happens is that all the other players that basically, you know, did their calculations supposing that they would have received your transactions are now screwed. So with this more complex design that is still not implemented yet, we hope that we are able to characterize this kind of very weird and complex interaction. Yeah, I think, yeah, again, you can do it with private information or not, but it's not really important. And yeah, I think that's basically it. And we are open for questions. Thank you. Do we have time for questions, by the way?
Yeah.
Cool.
I have a question. So first, an observation related to what I said before. There's also, thank you. First, an observation. I was reading some literature on computational social choice theory, and you know, didn't get very far. It was so heavily math laden, but it strikes me that's another area where there's you know, a library of mechanisms that's waiting to be put to more sort of like experimental
Okay, for the second question, I think this thing is still not scalable in the sense that it is in principle, but we are still lacking a lot of ergonomics. We are painfully aware of it, so there's still a lot of work to do. I'm not going to bullshit anyone in saying, like, oh yeah, this thing is super easy to use. That's absolutely not. It's still quite complicated. We just think that it's a better architectural choice that, you know, has more opportunity to scale. But it's still a pain in the ass to use today. Like let's be honest, okay? Wait, what was the question about that? Oh yeah, what we really need to do now is we really want to work very closely with people that are part of the MEV food chain infrastructure. Because, you know, we don't run any relayer, we don't have any RPC, we don't have a MEV product, we do not observe directly day to day how this stuff works. So there are some assumptions that we made. We made these assumptions talking to people and based on, you know, what we see around. But it would be very, very nice to work with, you know, people that are actively involved in this and they are willing to experiment with this kind of stuff. I think this is what it's needed the most for us at the moment, like really interaction with people that are in the MEV production infrastructure. Yeah, for sure.
He also asked if we have some insight from our model yet.
Yeah, I mean, there are, we have, I mean, some insights, yes, for sure. Even in this very simple toy model, for instance, you know, it was really nice to see actively how participating in different men pools and being able to observe or not observe some stuff would radically change your access to actually block space because of the order flow you can intercept. Yeah, we have some insights, but yeah, we are still like largely playing with this stuff by ourselves at the moment. So.
Would you mind just going back to the simulation results? Simulation results. And,
okay.
Yeah, and just talking through, because you mentioned that those payoffs and the costs are Bayesian results,
yep.
right? So you would basically say that in expectation, the cost would be 297 and the expected payoff would be 300.
Yeah, exactly.
But for the previous result, when you simulated, I think it was the second run, so with an exclusive order flow number one, you would have two agents having the same results, which is just something that I would wonder how this would work in practice. So
yeah, okay, no, so it was the second one, I think, because in this one, Builder
yeah.
is the only one that works.
Oh, exactly.
Yeah.
So with this, I have a question as well. So, like, what does it mean? Because why would this would assume that the builder number 3 would not change their strategy based on the information that they know about the other two? Because in the case when the first and the second would not bid because they know that there are no interesting transactions, builder 3 could say, I'm paying you only like a marginal cost, right? Because this would then include knowing having full information about the game, right? Keep in mind,
this is a simulation, it's not equilibrium checking. So with this strategy, it may totally be that Builder 3 could pay much less than 270 to secure this order flow, for sure.
Okay, yeah.
But at the moment we are, again, as I said before, now this is a small game and already finding equilibria will be a pain. So in general, the way we expect this to work in practice is, I mean, we know that builders and, you know, all this kind of stuff is not like really strategic. They are bots that basically execute some heuristics that are pre-programmed. So the idea is you can use this thing to simulate how profitable that heuristic is. And maybe you want to say, okay, now let's make a small change in the heuristic. Do I go better or worse? Yeah. I wouldn't expect to be able to like really do like gradient descent and find an optimum.
Okay, yeah. So this is so like if they would adapt the strategy based on information. Okay.
I mean, obviously, if you can rent a shit ton of AWS space, then probably things are different. But
well, you can do that.
And for the other result for the third run, I think it was, or for the second, where you would have two agents with the same amounts. This would just signal that. In your simulation, you would expect that both agents could pursue this strategy, but in the end, only one of them would be chosen to do the action, right?
Yeah, exactly. So the idea of the expected outcome is Imagine that you say I win like 100, but only 30% of the time. It's like saying, okay, now you're weighting that payoff by the probability. So I don't want to say something stupid, but I think the expected outcome would be 30 in that case. So yeah. Please.
Hi, could you give some insight into how you think privacy might affect the way players interact with each other? Like, usually who's hiding what from whom, and does this benefit certain players more than others, and how would you model this?
So if we go back to the model, I think that there are different ways of modeling private information here. One obvious thing is in the definition of a player, you can tweak this box here and this box here. And basically, this allows you to model, for instance, an agent that listens to multiple mempools. And so it can see more transactions in a way. When instead you really, there are various definitions of private information here. One is this one. The other one is, what do I know about how other players interact and what other players do? So this would basically have to do with this and with the auction parameters. So when you model the other players, imagine that you are a player and you are modeling other players, then you have to have some ideas of these two things. And obviously, the more you know, the more precise information you have, the more your model will be reliable. The third thing, if you are thinking about privacy, preserving mempools and transactions and stuff like that, then we go here that is still highly speculative, but the idea is that, again, I can give you some information like a lower bound of the MEV that you can extract from some transaction, but then in practice, if I decide to commit to show you my transaction, that could be much more, or actually could be that if you don't honor all the conditions I gave you, it's much less, if not zero. So again, it's very difficult to see how granular you want to be with these things, because more granularity also means less scalability. It will become more difficult to simulate this stuff. So yeah, we are trying to do trade-offs, basically. Okay.
Yeah, 2 minutes are missing, so the last question, if you have. If not, thank you.
Could you explain a bit more about, I guess, like the feedback part? Because I know, like, for example, some of the strategies, like, it may not just be like over one game, but like over a long game. Like, does the feedback just continually, like, I guess, affect the input over and over again? Because, like, in the example you gave about privacy, right? Like, let's say that a user sends a transaction and then, like, the builder commits to giving them, like, a certain profit, but then the builder defects and then they do something completely arbitrary. Does that just affect, like, the next round, kind of, and how do you simulate that?
Yeah, so basically the way you can simulate it is you have this I thing here. I don't know if I mentioned this in this workshop or in the previous one, but basically there are three main kinds of atomic games that you can use. They are strategic choices that are, you observe something, you have an action space, and you have to pick one thing that you can do, and you make a strategic choice. The other one is a deterministic function. So you have no strategy, you just observe and do. And the third one is draw from nature. So that is basically used to model random events, like flip a coin and stuff like that. So if this thing is a deterministic procedure, then the user can be sure that there is no strategic choice involved. So you can model, for instance, a player that cannot censor transactions by saying, these are deterministic functions. Players know this. There is nothing that they can do. And these would be the equivalent of like modeling a builder using, I don't know, like an FGX or some private like enclave of some sort. On the other hand, if you want to model something different, you could say, okay, this is maybe a random function. There's a draw from nature, and like 30% of the time, these builder scams you. And again, now the user observes the structure of the game and knows that, okay, I can commit to this player, but then I have to know that every time I decide to reveal, there is a 30% possibility that I get scammed. So again, you can basically bake this stuff into the model.
It's like, when you do the stochastic model, like, I guess, how, like, this is kind of weird, like, how far do you iterate? Because, like, in the example you gave, where, like, 30% of the time the builder like scams you, right? Then the user changes their input and that affects like the next simulation, right? So like, I guess how far can you like iterate until you reach, because is that similar to finding equilibria or?
Not really. Basically, what you do in this game is you go all the way to the end and then all the way to the other end. So you do all the red and then all the blue. These are all the actions, and then you have all the payoffs. And then you get the expected value for those parameters. The way you find equilibria and stuff like that is by performing small deviations on the strategy space and basically doing gradient descent. But that's why we're focusing on simulations more than on that, because that's going to be computationally terrible. Okay, I think we are done, but we will be around for more questions outside if you want. Thank you very much.